Greetings, my name is Juan Kim. I am a graduate student from the Department of Electronics Engineering at Sogang University, located at South Korea. It is a great honor for my opportunity to present about a recent study under the guidance of Professor Jiuk Jang. Today, I will brief you on throughput enhancement via exploiting parallelism for Hyperledger Fabric blockchain. Here is the overview for the presentation. First, I'll explain the background detail for Hyperledger Fabric blockchain and its effects on parallel processing. Then, I will propose three types of methods to overcome this problem. Last but not least, detailed explanation with our proposed methods and results for a specific example will follow. This slide shows the background detail for our main problem, Hyperledger Fabric key issue. Key issue occurs in Hyperledger Fabric private blockchain because of its unique parallel processing structure. It is an identification value in the database. It can be understood as an account ID, which may be adapted with various forms depending on the network situation. Transaction is similar in concept for almost all blockchains, which is a dataset of information, also in Hyperledger Fabric. Transaction in Hyperledger Fabric contains key values to distinguish source of where the transaction was created. Now, key issue happens when transactions of the same key overlap in a single block. With the identical value, transactions after the initial one will not be processed and marked as a failed one. Transaction failure would cause extra steps to resubmit back into the blockchain network, leading to throughput degradation. Therefore, our research focuses on how to avoid such situations. To further understand the key issue in Hyperledger Fabric, we must understand the structure of distributed ledger. This slide shows the unique distributed ledger structure of Hyperledger Fabric. It is configured with two parts, the blockchain with the overall transaction data, and the world state with the recent transaction results. Inside the world state, key is the identification value, followed by a version value. The version value of a certain key indicates the number of times transactions has affected the world state. If transactions and world state versions mismatches, it will not be reflected and be recorded as a failed transaction. This is called a multi-version concurrency control error, which is the cause of Hyperledger Fabric key issue, shortened as MVCC error. We will understand the circumstances where transaction version mismatch occurs and why this results to transaction failure on the next slide. The next slide shows the distributed ledger and consensus algorithm of Hyperledger Fabric. There are three steps in the consensus algorithm. At the first step, execute requested transactions are based on the initial world state information. In this slide, for example, 3 transactions are requested, all with the common key A, based on the initial world state where no transitions have occurred in the past. All transactions possesses version value 0 with different type of keys. On the second step, order, Hyperledger Fabric consensus mechanism gathers all valid transactions and sorts them on chronological order. With the current example where we suppose transaction 0, the fastest requested, and transaction 2, the latest, transactions altogether would be ordered by 0, 1, 2. The last step, validate. Transactions will be instantly reflect the world state one by one. When transactions affect state change in the world state, version value of the current key alters instantaneously. Only transactions with identical version will be a valid transaction and be processed through the world state. As you can see on the slide, the first transaction 0's version value matches the initial world state values, and therefore update the world state with the current transaction information by adding the version value to 1. Right after then, with transaction 1, transaction detail with the key C would just be fine. However, state change occurred with this key A. Therefore, key version mismatch occurs. It will not be reflected to the world state. This would be similar with transaction 2, since they have an identical key value of A. Now, we will be introduced to the solution that can handle such matter on the following slide. This is a proposed method, the dependency graph generation system. The main idea would be avoiding transactions with the same key entering the same block by information based on a tree structure. Transactions are sorted by time and key value to form a dependency graph, which will be then transmitted according to processing priority. On the left side of the presentation, we will suppose a pool of random transactions, where transaction numbers indicates the chronological order for easy understanding. Our proposed method would initially order the random transactions and sort them by time order. We can see how all the transactions are aligned in number. Then to form a tree structure, we add tree levels to transactions that have identical set of key values. On the slide, we can see transaction 1 has increased in tree height since it shares the same key B. After the sorting process, all transactions will be eventually form a tree structure where each tree levels are a division of key values. For example, if the transaction 2 had identical key set B with transaction 1, it would have formed a new tree level 2 since it collides with transactions 1 and 0. Based on the tree structure, which we will call the dependency graph, we will now understand how to process transactions by priority and 3 types of methods following by. This shows the transmission priority. Differs with the method that we would apply on, however, still share the same process. There are 2 main priority for processing. The first is that transactions on the root level has top priority for transmission. This would mean the lowest tree level on the dependency graph. After that, the second priority would be that transactions that has the fastest requested time would have higher priority than transactions requested after. We will show detailed steps on how transactions should be transmitted after explaining our different types of proposed methods. This slide shows the transmission methods of our proposed algorithm. It basically follows the overall priority just mentioned on the previous slide. Time method would be the example for the previous slide. This would be the most basic and simple method for transmission, since it processes transactions only with time priority. It has the lowest starvation rate. The next is the height method, where another priority factor is considered in between. After transmission priority of the root level is considered, the second priority would be transactions with the highest tree levels linked together. In other words, the biggest height value. For example, 3 transactions with the same key would form a dependency graph of maximum 3 levels in height. Therefore, the transaction at the root level would have a height of 3. Applying this height method would lower the overall height of transactions during transmission and result with high TPS rates. However, would bump into starvation problem since several transactions would be transmitted ahead of its original turn. The last method, height with starvation method, would be method in between time and height. This shares the same priority with height method, except starvation occurred transactions would have the highest priority, even higher than transactions at the root level. This method enables to maintain moderate rate of TPS while handling starvation problem that occurs during transmission. This section shows the result of our proposed methods. For clear result comparison, 10 transaction set forming a 5-level dependency graph shown in the slide will be used. Transaction numbers are according to requested time, which should be used as a factor for time priority consideration. Transactions connected with each share the same key value. For example, transaction 0 and 1 have different key sets, therefore does not connect with each other. Transaction 8 in the slides connects with two transactions, since the transaction itself could be a transfer transaction that has two key values. The upper side of the dependency graph is the root level and has most of the time the highest priority for transmission. Block size of 2 was applied for transmission process. This slide shows the overall step for the original Hyperledger Fabric method. It does not have a dependency graph to consider, where it only transmits transaction in chronological order. Failed transactions are instantaneously retransmitted for clear comparison. Two parts can be seen for the whole process: the dependency graph structure being transmitted with block size 2, and transactions being processed through the block at the bottom right side. Each set of dependency graph corresponds with the blocks containing the transactions processed. Let's look at the first step of transmission. The red dotted box indicates which transaction enters the corresponding block. Since the current original Fabric method only transmits transactions in chronological order, transaction 0 and 1 succeeds. The next step shows the occasion of key collision. Since transaction 2 and 3 are connected with each other, meaning that they share the same key, transaction 3 fails since key version mismatches, leading to a MBCC error. Following by, step 3 shows transaction 3 and 4 succeeding, where transaction 3 is resubmitted right after it failed. We can see all transactions being transmitted after a total of 8 steps, in other words 8 blocks, while 5 failure occurred during transmission. The faded blocks after the first step are put in for visibility of the whole transmission process. For each key sets, the transaction located at the top of the connection indicates the root level of the dependency graph. Now, with the same sets of transactions, we will show the result with time method applied. Two priorities are in consideration: root level transaction and the fastest request time. At the first step, 4 transactions are at root level, since transaction 0 and 1 are the fastest in the above 4. They succeed into the first block, 0 and 1. At the second step, 3 transactions are at root level. Since transaction 2 and 4 are the fastest in the above 3, they succeed into the second block. The third step, where only 2 transactions are at root level, they succeed the third block right away, with chronological order. Now at the fourth step, only transaction 6 is at root level. Therefore, only 1 transaction succeeds the fourth block, even though there is an empty block space. Step by step, all transactions are succeeded through, with a total of 7 blocks and 0 failure during transmissions, with 0 starvation. You can notice that block transmission can only occur in one type of tree level. Next is the result with the hype method applied. Three priority are in consideration: root level transaction, highest height level transaction, and fastest requested time. At the first step, 4 transactions are at root level. Since transaction 1 and 5 both have height value of 5, they succeed into the first block with chronological order because they have identical height value. If transaction 5 had height value of 6, the entering order for the first block would have been transaction 5 and 1. At the second step, 4 transactions are at root level. Since transaction 2 and 6 both have height value of 5, they succeed into the second block. Step 3 is processed the same way as the previous step. Now, at the fourth step, there are 3 transactions at root level. Since transaction 8 has height value 1, it initially gets processed into the first step of the block, followed by transaction 0 since it has a faster requested time. Step by step, all transactions are succeeded through, with a total of 5 blocks and 0 failure during transmission. However, 5 starvation of total occurred during transmission. The presence of starvation is obtained by comparing with the original Hyperledger fabric transmission. Last is the result with the height with starvation method. 4 priority are in consideration, where all factors are identical with the previous height method, except starvation occurred transaction has the highest priority. The first step process is similar as the method of height, except this time starvation point is applied to transaction 0. This is because in the original Hyperledger fabric method, transaction 0 was processed at the first block. At the second step, transaction 0 gets processed into the first base of the block, since starvation occurred during the transmission. Between the 3 transactions at root level, transaction 2 with the highest height and fastest arrival time succeeds in the next base of the block. Now at the third step, 3 transactions are at root level. Since transaction 3 and 6 both have a higher height than transaction 4, they succeed into the third block, with starvation point added to transaction 4. The fourth step, transaction 4 proceeds into the first base of the block, followed by transaction 7, located at the root level. Step by step, all transactions are succeeded through, with a total of 6 blocks, and 0 failure during transmission. Starvation occurrence was reduced by 2. We can notice that all 3 proposed methods have 0 failure, successfully preventing key issue by transmitting based on the dependency graph. The last slide shows the result comparison between the original Hyperledger fabric method and 3 proposed methods. Since all proposed methods prevent transaction key collision, significant enhancement in latency reduction took place. Comparing the result between 3 methods, height method has the highest TPS rate with 60% increase, while showing defect in starvation with worst case latency of 3 blocks. On the other hand, time method showed the lowest enhancement of TPS by 10% increase, while showing great performance of 0 starvation. Height method with starvation showed medium performance of the 2 methods, successfully maintaining low starvation rate where no transactions passed beyond 2 block delays. These results shows that the 3 methods can be used adequately depending on the blockchain network situation. We hope the execution of our proposed methods bring about practical solutions for development with Hyperledger Fabric blockchain. Thank you very much.